Okay, so hi everyone. Unfortunately, there was a technical issue with some part of or couple of parts of the recording of the lecture. So the third lecture, so I'm going to complement what I've deleted from the live lecture because of technical issues and do it here using the iPad. So the first thing that we'll do is the part 2 of the lecture, which is about analytic continuation, kind of one of the magics of complex analysis. Okay, so the part that we recorded in class ended by us defining the notion of a holomorphic function. So let's continue on. And in this unit, and in this part, I'm going to talk about analytic continuation. But what is an analytic function? So say our function W, it's a complex valued function, but it's defined on some open set, like for holomorphic functions. So such a function W is said to be analytic at U, or analytic where it's defined, if it has a power 6 expansion at each point of U, of capital U. Right, and this is why you need the openness. You need it around every little point, little u in capital U, you'll have some ball, some positive radius so that you can Taylor expand or do a power 6 expansion around that point. That's why you need the openness of capital U. Now, in real analysis, what happens is that you have examples of non-differentiable functions, but when you have differentiable functions that are not twice differentiable and so forth. In complex analysis, that doesn't happen. In fact, what happens is that holomorphic functions are equivalent to analytic. So saying the function is holomorphic at its domain U is equivalent to saying that it's analytic. And that's kind of crazy because it means that, that direction is crazy. The other direction is trivial. It means that once you know that you are differentiable at a point, you can actually tailor at every point in U, in capital U. It means that around every point, you can also do a Taylor expansion. Particularly, you have derivatives of all orders, of any order. So once differentiable, complex analysis is actually twice differentiable, and therefore, by extension, has nth derivative for any n. So in a sense, holomorphic functions are much more rigid than differentiable functions as real valued in the real analysis setting. Okay, so that at the end of the day, it all boils down to the fact that there is this extra multiplicative structure, which is captured by the Cauchy-Riemann equations and make the holomorphic functions kind of more rigid. It's harder to be holomorphic because you see it implies that you are differentiable of any order and analytic. Okay, and if you want to have some examples, then polynomials in Z, particular 1 and Z are holomorphic and obviously analytic because this is the Taylor expansion of Z around 0. It's kind of a closed property. If you have two holomorphic functions, then also their sum, product, ratio, as long as G is non-zero and composition is holomorphic. Non-examples, which may be surprising, but we talked about it, I think, are the absolute value. And these are functions that look very simple, but they are not holomorphic. And everything that kind of breaks down the complex value to its two parts in a sense. So the real part of Z, the imaginary part of Z, the absolute value, as I said, and the conjugate function also. Everything that kind of tries to do something to the real or the imaginary part while not doing it to the other. Okay, so that's that. And again, that's a theorem. That's an important theorem that is useful when you start proving things. Usually what happens, you take holomorphic functions and you say, I can do analytic expansion, and then you work with that expansion, like proving the basic theorems. But that's not the issue. The interesting part, and that's kind of a very surprising aspect of complex analysis, is analytic continuation. So let's talk about that. And here's a kind of a toy problem. Say I'm giving you this function, g of z. Right? G of z is the sum, infinite sum, and goes from 0 to infinity, z to the n. And we all know it converges as long as the modulus of Z is strictly smaller than 1. And let's call this set D. It's an open set. And right, and it's, it is the power 6 expansion. It is a power 6 expansion, so it's holomorphic. And you can also expand it around every point in D. So it's a holomorphic and analytic and therefore holomorphic or vice versa function in D. But now what I want you to do, what I'm asking you is, please evaluate G for me at Z equals 1. And while you're at it, evaluate it at Z equals 2. Okay? But then you'll say, I cannot do that because I really cannot evaluate G at 1 because I'll get a sum of infinitely many ones. And I certainly can't evaluate it at 2 because I'm even getting a kind of a larger sum of exponentials, right? It's, it's everything is as bad as the other, but the 2 case seems worse than the 1 case. Right, so that's like the answer that you should give someone that asks you to do that. But then you can be remembered that you actually know this thing, and this is so these things in the domain D, in the open set D, actually agrees with this function, 1 divided by 1 minus Z, which you can evaluate essentially everywhere except for Z equals 1, right? So if you ask me to evaluate G at 1, then kind of cheating and looking at 1 divided by 1 minus Z won't help you, but now you can evaluate G in a sense at 2, because you found some other function that agrees with G on the domain of which G is defined, D. But that new function, 1 divided by 1 minus Z, is actually, you can evaluate it at 2, not at 1 still, but at 2. So in a sense, G of 2 is minus 1, right? Well, of course, that's nonsense because there are many functions that you can come up with that extend G, right? I mean, even if you restrict yourself to continuous function, for every value that you would like, and maybe 5, you can come up with a function that extends G, namely it agrees with G on the domain D. It's continuous, so it's kind of nice. And at 2, it attains the value that you want, say 5. Okay, so there is no meaning to saying, well, I'm familiar with another function that extends the function that you started with, and that new function that I'm familiar with, or maybe old function that I'm familiar with, I can evaluate that too. So maybe I should say that the answer to the original question was, evaluating that function at 2. So the problem is that there is no uniqueness, right? But, and that's the crazy thing, it turns out that actually, sure, restricting to continuous functions, there are many functions that extend G, but if you restrict yourself to analytic or holomorphic, same, functions in some domain that contains D, some domain that you want, in particular, some domain that will contain 2, the point you want to evaluate at. If you ask, if you restrict to analytic functions, if you require analyticity, then it turns out that actually 1 divided by 1 minus Z is the unique function that is analytic and extends G. Okay, and so if we restrict to analytic functions, there is a sense in which 1 divided by 1 minus Z is like evaluating 1 minus 1 over Z at 2 is essentially the right answer as far as analytic function goes to the question, what is G of 2? Okay, so in a second or a couple of slides, I'll try to be more formal but and more general, but for that particular example, what I'm trying to say is that, and that's kind of crazy, is that G of Z, that function that we started with here, determines 1 over 1 minus Z. Namely, if you ask what is the analytic function that's defined, say, at the entire complex plane excluding 1, or even at some ball that contains 2, because I want to evaluate a 2, but also contains, of course, the original ball D, so some ball around the origin of radius at least larger than 2. And you ask, what are the analytic functions that extend G? When there's only one such function, and it's this one. So in a sense, it wasn't your choice. It's not because you knew this this expansion, this geometric sequence and you figure out that. It's not something about you. It's not that you know this series and therefore you know a function that can work out. There is a unique function, and in a sense there is a unique answer to what is g of 2. So like information theoretically, 1 divided by 1 minus z was already kind of inside the belly of G. It was just maybe hard, in this case it was easy, to figure out which function is that unique analytic function that extends G, but it was always there. Information theoretically, G determines that function. Okay? Good. So let's stick with the example and not continue to the general discussion for now, for a second. Right, so that's what I just said. Turns out that 1 divided by 1 on Z is the unique way of extending G beyond D. And therefore, you know, the local view that you had of, I mean, with hindsight now, looking at this function, the local view that you had, namely the sum of Z to the N, this local view actually it's a local view, but it contains all the information of the global function. And of course, you know that, but maybe I could have started with looking at, you know, now that I know that this is kind of the answer, I can tailor expand this function around, say, -1, right? So this is what I'm looking at. And if you expand around -1, then it turns out that the expansion is the one that is given here. And now if I would have asked you, you know, evaluate this function at 2, it might have been harder to figure out that 1 divided by 1 minus z is actually what's hidden, kind of the global function, analytic function that of which I get a local view, namely Taylor expansion around -1. So sometimes it's kind of hard to go from the local view to the global view, but if there is a way, it's going to be unique if you insist on analytic functions. Interestingly, and again, before moving to the general setting, you can pick up other points, of course, any point that you like, but in a sense, you can also pick up the point at infinity. So what do I mean? So let's look at our function. So now with hindsight, we know the big global function, 1 divided by 1 minus z. Let's look at this function. And let's do some arithmetic massage to it. So first of all, I'm going to take 1z out here and then do this, okay? And now the point is that now, you know, if z is larger than 1, so actually if I'm outside of D, then this thing has a modulus which is smaller than 1. So this is a geometric series that converges, and you can write it like that, right? And you can also clean it a little bit by putting z inside, or you can start from n equals 1 or what have you, but you get this thing. And this, strictly speaking, is not a Taylor expansion, because strictly speaking, infinity is not a point in the complex plane. But other than that technical point, this is a Taylor expansion, or that's the name we are giving for it, at infinity. Right, so for us, saying, and there is a formal way of actually treating this, but for us, when I'm saying a Taylor expansion around infinity, I mean just a series in terms of 1 over z, right? So it's an expansion in terms of 1 over z. And so this is by in our language, a Taylor series expansion around infinity. And right, also from here, you can see here, you can actually evaluate z at this thing at 2, and you should get 1 or -1, right? Because you get minus, you know, 1 half plus quarter plus so forth. So you see, you have all of these local views. You have around every point, you can have a local view. And also, in a sense, around infinity, you have a local view. And what I'm saying is that, at least in this example, each local view like that actually determines the general function, like the function that is defined maybe outside of the domain of each of these local views. And it's information, theoretically, all the information is already within the local views, but like computationally, it may be difficult, or sometimes they're just not going to be any simple way of writing the general function, like the global function. Let's now consider the general case. And the actual theorem that we will care about is what's called the identity theorem. But first, let me give you a definition. It's a standard definition of what is an accumulation point. But just in case you don't remember what it is, let me say what it is. So say you have two sets, one contained within the other. So D is kind of the ambient set, and M is some set inside of it. It could be any set, not open, you don't have any requirements there. And we are going to say that a point P in D, in the big set, is an accumulation point of the small set M if, informally speaking, you can get as close as you want using points of M to P. Namely, for any distance that you would care about, epsilon, you can find a point Q in M. Maybe it's this one, maybe epsilon is this distance or something. You can find a point Q in M whose distance from P is at most epsilon. Put differently, if you'll take for any radius, for any ball around P, maybe for every radius, positive radius R, if you take a ball around P, it will contain points from M. Okay, it's the same thing. And that point will be Q from before, epsilon is R, and so forth. So for example, if P is in M, it's an accumulation point, but even if it's not, but points that are kind of outside of M and in a sense are on the boundary of M are the accumulation. These are exactly the accumulation points. Okay. So that's accumulation point. And the really weird theorem is that will support what I was talking about before about the identity, about the analytic continuation. We'll talk about that, is the identity theorem. So what does the identity theorem tells you? Well, say you have two functions, holomorphic functions, f and g, on a common domain D. And I'm going to need to assume that D is open because these are holomorphic functions. This is kind of by definition. And I'm going to assume that D is also connected. So there is like a formal definition of connected, but everyone kind of understand what it is, right? You can arrive from every point to any other point inside D by a kind of a continuous function. You cannot jump. So if this set is not connected because there's no way of moving from here to here without kind of jumping. But let's keep it intuitive. Set is connected if you can reach from one point to another without in a continuous manner. Okay, and sometimes an open and connected set is called a domain, but it's kind of confusing because domain is also the thing the function starts from, like the input of the function. So let's not use that terminology. And okay, and let's assume that E stands for equal, which is exactly these are exactly the points in D in which F and G agree. Let's assume that has an accumulation point in D. Okay? In D, not outside of D. Then by only knowing that, namely that F and G agree on some sequence that has an accumulation point, the identity theorem tells us that actually F and G agrees everywhere on D. Right? Which is indeed crazy. You have like, this is D, and maybe you have some sequence like that with an accumulation point inside D, and F and G agree only on these points. Knowing that immediately tells you that F and G actually agree everywhere, even on like very far apart points. Right, that's like, Aleph FS information suffices as long as you have an accumulation point to argue about like Aleph agreements. And in particular, and that's actually the way you usually use it, because an open set has a non-empty open set has an accumulation point, then if you know that E is an open set, Namely, if you have, if you know if E is an open set, namely, if the F and G agrees on some open subset of D, then immediately they actually agree on the entire set D. Right, so it's kind of easier to work with, but it's less, I mean, it's a corollary, so it's less surprising. Maybe it is surprising, but less surprising is that if you have this function, you have this domain D, and you have two functions there, and somewhere here, you know that F and G agree, but that somewhere is an open set. Doesn't have to be connected, by the way, just D has to be connected. So if E is an open set, then, and you know that F and G agrees on this small open set that you kind of understand better, then you immediately get that they must agree just by being holomorphic on the entire set D. Okay? So to use the words of Richard Bocher, the kind of holomorphic functions are very rigid. They are not floppy. If you know how they behave somewhere, then they are completely determined whenever they can be kind of defined or extended to. Whereas in real analysis, you know, if you know some derivatives, or if you know you have a differentiable function, and you know how it behaves somewhere, it doesn't mean you know how it behaves everywhere. Good. So a corollary from that is what's kind of usually referred to as analytic continuation. I mean, there is more to it than that, but I'm just going to you know, take what I need. So so suppose you have a function f which is holomorphic on an open set V. So it's this small set. And let's say that V is connected, V is contained in a larger set U that's open and connected. So I think of V is an open set in which I kind of understand F. Maybe I did Taylor expansion, maybe somehow I can understand F somewhere, but not everywhere, or not everywhere I want to. But and U is kind of the set in which I want to understand F. I want to figure out what's the evaluation of F here also, not just in V, which for some reason I can understand better. Then the theorem is, it's a theorem. When the theorem is a corollary from what we did, so I don't say this is a theorem, but the point is that there exists at most one, not always there exists one, but there exists at most one way to extend F to a holomorphic function on all of U. Right, because I mean, if you had two ways of doing that, G and H, these are two holomorphic functions on U, which agree, each of them agrees with F on V, then by the identity theorem, because V is open and I guess, of course, non-empty, it has an accumulation point, and therefore G and H, you know, on the account of F, because they agree with F, they also agree with each other, and therefore they agree on an open set and an accumulation point, and therefore they agree on the entire set U, right? So there is only one way to extend F analytically, if at most one way, and the unique function, if it exists, it's called the analytic continuation of F to U. Okay. Now, the grown-up way of thinking about it, and it's kind of incorrect technically, but it's just to call, instead of calling the function F on VF and the function that you extended F to, the analytic continuation of F to U, instead of calling it like that, let's just call it F. Because you see, I mean, I know the domains are different. I'm aware of the definition of a function, but the point is it's really the same function. It's just that you didn't know a priori how the function behaves outside of V. But it's the same function because F when restricted to V, or F that you started with, actually uniquely determines the global F at U. So analytic continuation is the right terminology, but really what you should think in mind is that it was F all along, and you just understood F at some particular open set, small open set, rather than everywhere. So maybe in our example, right, so we had this G of Z, which was the sum of Z to the N, and I have a picture here. So we know, because we kind of know things from high school, that 1 divided by 1 minus z, well, it's analytic everywhere in the complex plane except for 0. It's also not so bad. It has what's called a simple pole there. It's not that a crazy bad behavior. And that extends, this function that we started with, but really, in a sense, these two functions are the same. From this function, global function, you can infer of course, just doing tailor expansion, you can infer the smaller function, the local view of the function, but also from the local view of the function, conceptually, maybe not computationally, you can get back to the global description of the function. There is no loss of information. So just, before we'll continue talking about branch cuts, which I think actually that was captured well in the video in the class, so I'm just going to upload that part there. Let me tell you what's going to happen in our case. So in our course, what's going to happen many times, in particular next time, is the following. This is the complex plane. We are going to have some function that is defined on the upper half, on the upper half of the complex plane, namely all complex numbers with imaginary part positive. And that function is going to be given by some integral. It's going to be the Cauchy transform. It's going to be something that will look like that. Never mind that. But, just so that you have a function. It's kind of a weird looking function. It's this function that tries to encode some measure. Okay. And that function, again, is defined. It's going to have poles on the real line. And therefore, we don't want to mess up with the real line. So we only consider it as a function on the upper half plane. And what will happen is that we will not quite understand this function very well, but if we go around infinity, and in particular, if we kind of go far enough, maybe someplace here, then that function, we can actually, this g of z, the Cauchy transform, we can actually Taylor expand to get some Taylor expansion. It's going to be Taylor expansion around infinity, like in the sense that we talked about before. Right, so this is a complicated function, but around infinity, it will take a simpler form. It's going to take essentially a Taylor expansion where the coefficients are going to be the moments of this distribution. We'll see. Now, the point is that we are going to understand the moments of the distribution so well that we are going to be able to say something non-trivial about this thing. We will know some recurrence relation between the moments. Actually, the moments are going to be the Catalan numbers in the example that we'll have. So we know some recurrence relation about the Catalan numbers, and that will enable us to say that, well, this function has an analytic continuation. Or actually, what we'll say is that this function, this function solves some quadratic equation. And if you will solve that quadratic equation, you get two solutions. One of them is completely irrelevant. So the other one is actually going to, you look at it, it's going to look like something like this. Never mind that. Or something like that. This is z, and this is 2. And that function, when you look at this function, you say, well, actually, that function is defined not just around infinity, and actually, it's also defined on the real line, on the real axis. Well, I mean, right, this should be like 4 minus z squared. So say you have -2 and 2 here. So that function is going to define in the real axis. So this is an analytic continuation because it agrees with this thing somewhere, not only of that local view of the Cauchy transform that we started with, but it's actually going to extend the Cauchy transform itself because you can now evaluate it at the real line. So that's how we're kind of going to play with analytic continuation. We are going to start with a function is going to be the Cauchy transform. Then we are going to go far away to infinity, so the moments of the measure will kind of come about. Using info understanding, usually combinatorial understanding of the moments, we'll be able to say non-trivial things about this essentially generating function. And solving that will give us a function that has a simpler form. So this one in this case. And that function agrees with that function and definitely with that function, but it extends it because you look at it and you see that it's defined on a larger domain. And that's the way we are going to use analytic continuation. We're going to kind of looking at local views to get some interesting information and infer things that it was very difficult to understand a priori that this function or that function satisfy. Okay, but that will have to wait. So next up is the branch cuts, which actually I covered in the actual recording, and we'll continue from there.